All right, let's talk about some of the things real quick we do with radian measure. A lot of it we'll have to do right now with circles. We'll expand that as we go along. But this circle, for example, has an internal diameter of 7 inches, so it's 3.5-inch radius. So we've got a nice 3.5-inch radius circle. We'll make it better. So we've got a 3.5-inch radius circle. And if we want to put an arc in here of just by any measure, let's say that is 1.3 radians. Now I could put a round at the end of that if I wanted to, but without a label, angle measurements, if they don't have units on it, they are presumed to be radians. If you want degrees, you have to put the degree symbol. But if it doesn't have a unit, it's presumed to be radians because it's a ratio. We talked about that in the other video. Let's say we have a radian measurement for clarity. The nice thing about our definition, if we have really any two of these pieces of information, radian measure for the angle, radius of the circle, called inside the circle, we have any two of those, we can find the third, in this case, arc length. So if we do arc length and radius, we can find radius, and certainly if we do arc length and radius, we know how to find radius, which is the ratio. So that definition of radians, being the ratio between arc length and radius, just a little bit of algebraic manipulation, gives us one of our first formula for radian measure, or first circle formula in radian measure. If we want an arc length, all we have to know is a radius and how much angle we go through. So if we want that arc length, we've got 3.5, again that's 3.5 inches, times the 1.3 radians. All we have to do is find that product. Now, what's that product? We have calculators. You should probably be able to do that nice and fast, but I don't. So I'm stuck. Now, 4.55. So nice 4.55. So nice 4.55. Now, again, what are the units on that? Well, we've got feet times radians, which, as we talked about before, radians don't contain units. So that product being 4.55 feet. Hopefully that seems nice. We could also, again, do that if we say, knew how much arc we were putting out here, say it's 2.5 inches. So sorry about that. So if we have a arc length here of, say it's 2.5 feet, and we want a particular radian measure, or say we want a particular radii, whichever piece of information we're given, we can find the other one. So let's say we know we want this radian. You can be something nice. Say we want to be pi over 4 radians. It's not necessarily nicer than 1.3, but sometimes we'll see radian measures in factors of pi when they're even cuts of the circle, and sometimes we'll see them as decimals like this, depending on what kind of information we're dealing with. But if we then want to know what this radius is, Well, we have our relationship. We know that the arc length is equal to that radius multiplied by the angle as long as the angle is in radian measure. If it's not in radian measure, we have to convert it to radian measure. So the 2.54 is equal to the radius times the pi over 4. So multiply both sides by 4 and divide by pi times the 2.5 is our radius. So if we wanted an exact value, that would be what? 10 over pi is the radius. So 10 over pi. And again, this is feet. We've taken feet and divided by this ratio. So it stays feet, which is nice. So 10 divided by 5 feet. Okay, somewhere around 3 feet if we want to be, get a decimal approximation, but often at 10 over pi, the nice exact value, often that's exactly where we will stay. So this arc length formula, arc length is equal to r theta, is a very handy geometric formula. Bad part about it, it only works if our angles are in radians. The good part, we can put our angles in radians. So we get this nice handy formula for it. And really, this formula is just a slight manipulation of our definition of what it means to be radian measure. So, a new piece of paper here. And I want to talk about a very cool extension of this formula. I'm coming to the circle, so I'm going to give myself a circle. Make sure that that's a good spot. And I want to take this same arc length formula and kind of modify it a bit and see if we can do something, kind of extra. So right now, we know that if we have an arc length S, that's equal to r times theta, with the restriction that that angle theta must be in radians for this to work. So if I say approximate our center here, and we gave ourselves some radius r, this thing has a radius of about 9 inches. And we went through some angle here. Let's say we make an angle of 60 degrees. We could compute the arc length along the edge here, S. So just for practice, let's do that. So we have S equals our radius of 9 inches. And our angle is where we have to be careful. We can't use that 60 degrees. If we did, we'd have inches times degrees, and that would give us inch degrees. So inch degrees over here. If we multiply that by 50, 540 inch degrees. So that arc length is 540 inch degrees. And I still don't know what an inch degree is. Hence the disadvantage of measuring in degrees. But if instead we take that 60 degree measure and turn it into pi over 3 radians, because pi over 3 radians is a ratio unit, it doesn't contaminate our inches. So take that as, divide those 3's out, and you get a nice exact answer of 3 pi inches, which is a little more than 9. So this length here would be a little bit more than 9. And if you remember our discussion on radians, if it was exactly 9, that would be 1 radian. Pi over 3 is a little bit more than 1 radian. So should make sense that that's a little bit more than none. But what I want to do to kind of extend this is take it out of being a static problem. Take out the idea that this radius, okay, we're going to keep the radius fixed. But instead of having this angle be some fixed angle, and this arc length be some fixed arc length, we're going to let this thing move. So instead of having some, nice angle that's going to stay in place, I want to take initial side. I'm going to draw that in roughly standard position for the fun of it. It doesn't have to be. Remembering that our radius is still at 9 inches. But instead of going through some static angle, I'm going to go through some angle over time. So let's say instead of that pi over 3 radians as the one motion, let's say we go pi over 3 radians for 1 second. And then another pi over 3 radians, another pi over 3 radians in 1 second. And we keep moving at about that speed where we go through, pi over 3 radians about every second. If we do go through that pi over 3, I'm going to write that down, radians per second. If we do go through pi over 3 radians per second, what does that tell us about how fast that edge is going? Because this radians per second is a speed, but it's a rotational speed. How fast is this thing spinning? If I want to take that rotational speed and turn it into a linear speed, how fast is that edge going in, say, feet per second, or in this case, probably inches per second. By the way, inches per second is a linear speed because inches is a measure of length. It doesn't have to be going in a straight line. It's going along a curve. So sometimes people get unsure about calling it a linear speed. It's a linear speed because it's a linear measurement. So this rotational speed here, which we'll just call angular speed, which is going to be angle in radians divided by time, in this case it's seconds. And we tend to use the Greek letter omega for it. Looks a lot like a W, feel free to call it W, but it is the Greek letter omega. And if we want to get that angular speed into a linear speed, inches per second, of how fast that's moving, we essentially use this relationship. We know that a fixed arc length is going to be equal to the radius times the angle we go through. So if we have this angle go through some of the radians per time, then that's going to make this arc length go through so much arc per time. We're almost just dividing those sides of that equation by 2. That means our formula changes to r omega, our radius times our angular speed, being equal to arc length over time. This is like inches per second. That's a velocity, v. So this v equals r omega. Yeah, it's a new formula for us for linear velocity versus rotational speed on a spinning object. It's essentially just a modification of this S equals r theta, our arc length. So if we have this thing rotating with an angular speed of pi over 3 radians per second, and we want to find out what is that linear velocity, how fast is that edge going? Well, that linear velocity is 9 inches out and it's traveling at pi over 3 radians per second. Well, gosh, those just cancel again, and we get 3 pi inches times the radians is again just inches per second. So actually, the same calculation we have up here, because instead of moving this speed just once, it's moving that speed every 1 second, so it goes this distance every 1 second. Now, that's nice, might be kind of a boring result. Let's do one that's a little bit more interesting, but that's the idea. So let's say instead we want to speed this thing up, have it spin quite a bit faster here. And instead of looking at this big circle, I want a much smaller circle. So that's fast. So we'll take that smaller circle near the middle of my rotation here. That's better. So the outside of this, quite a bit smaller, the outside of that is about, measure. Yeah, that's about 1.5 inches. So the radius of the whole orange circle is about 1.5 inches. I'm going to go 3/2 inches, just for simplicity. Fractions are easier to work with in the long run. And I want to imagine this thing is spinning really fast. So let's say this thing is going to spin super fast. If it does, we often don't talk in language in terms of radians per second. You might be more used to hearing people talk in RPMs. And RPMs are rotations per minute. So let's say instead of being given radians per minute, which would be handy, we're given the more common rotations per minute. Let's see this thing is spinning, how about 300 RPMs? So 300 rotations per minute. So that 300 rotations per minute, it gives us an idea of how fast this thing is spinning. But to use our formula, our velocity equals r omega, or linear velocity equals r times angular velocity or angular speed. To use that, we have to turn this rotations per minute, this RPMs, into radians per time instead of rotations per time. But the nice thing is, we know all the pieces we need to do that. That 300 is, as we said, 300 rotations per 1 minute. And if we want to turn that into radians per minute, we just have to get rid of rotations and put in radians. And to do that, all we have to do is know how many radians are in a rotation. So how many radians are there in a rotation? Well, we've talked about that. There are 2 pi radians in 1 rotation. And if we calculate that, that's going to turn it, after the rotations cancel, turn this into radians per minute. Well, we can stay with radians per minute and do radians per minute. That is an angular speed. But while we're here, why don't we turn those minutes into seconds just for practice? So if we want to turn these per minutes into per seconds, we have to get rid of minutes. Minutes is on top now, so they'll cancel. Get rid of minutes and put in seconds. Again, all we have to know is how many seconds are in a minute. Ideally, we know that. And then our minutes are going to cancel. Now all we're going to be left with is radians per second. And you don't have to be per seconds. I'm just using per seconds here because they're nice. But we could do angular speed in radians per K, radians that time unit matches the time unit we're using on velocity. So straight line velocity. So as long as those match, we can use any time unit we want. Seconds are nice. So I'm going to go with that. So I'm going to clean this up a little bit first. Let's see. The times cancel, 6 goes into 35 times. So that'll be 10 pi radians per second. So that's pretty fast. Every second it's going through 10 pi radians. 2 pi is a rotation, so that's 5 rotations per second. This thing's spinning pretty fast. 300 RPMs is pretty fast for a little over circle anyway. Once we have it in radians per time, this is in omega, it's an angular speed. So we can use it in our angular speed formula. So that linear speed is our radius. We said the radius was 3 halves inches. So 3 halves inches, we'll fill in spinning circle. So 3 halves inches times our omega 10 pi, and that's in radians per second. So this is inches times radians per second. Our result is going to be inches per second. Again, because radians are a ratio unit, they don't contaminate our units in calculations. So cancel those, get a 5, and we've got a nice 15 pi as our linear speed. So 15 pi inches per second. Now, if we wanted to convert that to feet per second, because we like feet per second, we certainly could. We know how many inches are in a foot. We could turn it into miles per hour if you wanted to. Or inches into feet, feet into miles, seconds back into minutes, minutes into hours. We could turn this into anything we want. I'm going to tend to leave the 15 pi, because 15 pi is a nice exact value. Well, if we want to approximate it, 15 times pi is somewhere around what, between 45 and 50. So the edge of this circle, as this thing spins really fast, the edge of that circle is going somewhat less than 50 inches per second as it spins around. So we get a very nice relationship between our rotational speed and our angular speed coming from this very nice relationship between arc length and radius that came from our definition of radius. So these are some of the reasons why we like working with radians, because it makes a lot of these calculations surprisingly nice. Now, if you go out there, you'll find formulas that will take degrees in them, formulas for area of a sector. You can find these rotational formulas in terms of degrees as well. But if you look deep into them, you will usually find somewhere in that formula is the conversion that is turning that degree measure into a radian measure so it can be used in a formula. So I often, talk to people who are like, I don't like radians, I don't ever want to use radians. I have these nice formulas. If every single one of those formulas converts their degrees into radians anyway. So learning how to use them kind of raw to make your work more efficient is going to be handy, particularly for those of you going into physics engineering, calculus, that sort of thing. Radians get used more and more often because really they mean a lot more than degrees do. Okay, so play with these formulas. There's some nice things about bolting a sprocket onto something or connecting things with belts. Sprockets conserve how fast things rotate. So if two things are bolted together and they're rotating together, like these are, then they're rotating at the same rotational speed. So omega will be conserved. If two things are connected with a belt, a chain between these two, that makes the linear speed of this edge the same as the linear speed of that edge. So the v's are conserved, but the other will change. So if you have some problems messing with those, let me know if you have any trouble with them. And well, we'll talk more about these tools when we get together. Have a good day.